Welcome to the Explainer. Today we're going to take a trip, starting from the physics we all know and heading straight out into the cosmos. We're digging into gravitational potential and gravitational potential energy. And trust me, by the end of this, you'll see why the simple stuff we learn in school needs a serious upgrade when we start looking at the planets and stars.
But let's start with a puzzle. You lift a book, right? Its potential energy goes up. It's positive. Easy enough. So why, when physicists calculate the potential energy of our own moon, do they get this enormous negative number? How is that even possible? That paradox is exactly what we are going to unravel today.
So to get to the bottom of that mystery, we've got to look at why the rules we use down here on Earth just don't cut it once you get into space. And that means we need to start with the formula we all probably remember.
Yeah, this one. The classic mgh. Potential energy is just mass times g times height. And look, for everyday things, it's perfect. A falling rock, a ball you throw, the pencil you just picked up. It works flawlessly. The higher you lift something, the more positive energy it has. Simple.
But here's the catch. The mgh formula relies on two big assumptions that completely break down in space. First, it assumes g, gravity, is constant. That's fine if you're just a few feet off the ground, but for the moon, the force of gravity gets way, way weaker the farther out you go. Second, it assumes the ground is our zero energy point. But if you're comparing Earth to Mars, which ground do you use? It's not a universal system.
To make physics work everywhere, for everything, we have to change how we think. We need a new zero point, one that isn't tied to any specific planet, but works across the entire universe.
And here is the absolutely brilliant solution physicists came up with. Forget the ground. The new zero point for potential energy is infinity. Just picture an object so mind-bogglingly far away from any planet or star that it feels zero gravitational pull. It's totally free. That spot, at an infinite distance, is what we now define as having zero potential energy.
So if the absolute maximum energy an object can have is zero, way out at infinity, what does that mean for everything else? Well, think it through. To pull a rocket away from Earth, you have to fight gravity. You have to do work, which means you're adding energy to the rocket. So potential energy increases as you move away. But wait, if the energy goes up as you move away, and the highest it can ever get is zero, then that means anything closer than infinity must have an energy level below zero. It has to be negative. And that, right there, is the whole key.
Now this leads us to a really important point. Physicists use two terms that sound almost the same, gravitational potential and gravitational potential energy. They're not the same thing, and knowing the difference is crucial. First, you've got gravitational potential. You'll see it written with the Greek letter phi. The best way to think of this is that it's a property of the gravitational field itself. It's like an energy map of space. It tells you the potential at any given point whether there's actually an object there or not. It's the work needed per kilogram to get to that spot from infinity.
And the formula for it is beautiful and simple. Negative g times m divided by r. G is the gravitational constant, big M is the mass of the planet making the field, and r is the distance. See what's missing? There's no little m. This value is all about the location in space, not the object.
Then we have gravitational potential energy. Now this is different. This isn't just about the location. It's the actual energy a specific object, like a satellite or the moon, has because it's sitting at that point in space. It's personal to the object.
And the formula shows this perfectly. It's almost the same, negative g, big M, but now we have little m, the mass of our object. So here's the simple connection. To get the potential energy of an object, you just take the potential of its location, that phi value, and multiply it by the object's own mass. That's it.
A fantastic way to visualize all of this is with an idea called a potential well. Imagine space is a giant stretchy rubber sheet. A huge mass like the Earth or the Sun creates a deep dip in that sheet. Way out on the flat parts, that's infinity, where the potential is zero. But as an object gets closer, it falls deeper into this well, and its potential gets more and more negative. In fact, all of us right now are living deep inside Earth's potential well.
Okay, that's enough theory for now. The real test of these ideas is what we can do with them. So let's put this into practice and solve a couple of cosmic scale problems.
All right, check this out. We've got a 200-kilogram rock. It's starting from way out in deep space, basically at rest. It gets pulled in by a planet's gravity and starts falling faster and faster. The question is, just how fast is it moving right at the moment before it smashes into the surface? To figure this out, we use one of the most powerful rules in all of physics, the conservation of energy. The rock starts with zero total energy. As it falls into the planet's gravitational well, its potential energy drops, becoming a big negative number. But energy can't just disappear. To keep the total at zero, that lost potential energy has to turn into something else. And it does. It turns into the energy of motion, kinetic energy. So the kinetic energy gained has to perfectly equal the potential energy lost.
So, you plug in the numbers for the planet's mass and its radius, and you get an impact speed of 4,385 meters per second. That is almost 10,000 miles per hour. And we calculated that just by knowing it started from far away. That shows you how powerful this concept really is.
Okay, let's try another one. This time, we're asked to compare the gravitational potential at the surface of the Earth and the Moon. In other words, how deep is Earth's potential well compared to the Moon's?
Using our formula for potential, phi equals negative gm over r, the results are pretty dramatic. At Earth's surface, the potential is negative 62.5 megajoules for every kilogram. On the Moon, it's only negative 2.8. Earth's potential is way more negative.
And this isn't just an abstract number. It has massive real-world consequences. Earth's potential well is over 20 times deeper than the Moon's. That number tells you exactly why you need an absolutely enormous Saturn V rocket to escape Earth's gravity, but the Apollo astronauts could lift off from the Moon with a tiny little engine on their lander. Escaping a deep well takes a lot more energy.
All right, so we've seen the theory and we've put it into practice. Now let's look at how this stuff shows up on exams, because understanding these classic problems is the best way to make it all stick. A super common question is all about escape velocity. That's the speed you need to break free from a planet's gravity and never come back. Think of it like this. Being in the potential well is like being in energy debt. To escape, your kinetic energy, your energy of motion, has to be big enough to completely pay off that negative energy debt and get your total energy back up to zero.
And when you do the math, when you set the kinetic energy equal to the potential energy, it simplifies down to this beautiful, elegant little formula. The escape velocity, v, is just the square root of -2 times the gravitational potential phi. It's a direct connection. The deeper the well, meaning the more negative phi is, the faster you have to go.
And that brings us full circle. We have all the tools we need now. A minute ago, we calculated that the potential at Earth's surface is negative 62.5 million joules per kilogram. So, here's my final question for you. Using that elegant little formula we just saw, how fast would a rocket need to go to climb out of that well and escape Earth's gravity? Forever. It's a calculation that ties everything we've talked about together. Thanks for joining this explainer.